there is an upper limit to the strength of interactions in quantum field theory, that interactions cannot be arbitrarily strong, otherwise you start violating very fundamental principles. And so what we're going to do is we're going to do this exercise using something called the bootstrap framework, which I'm going to explain, and we're going to try to maximize interaction strength. And when you reach this upper limit, we're going to look at the observables that we're going to get. We're going to look at cross sections and things like that are measured experimentally. And the hope is that we can see something that we see. In particular, that we can describe some aspects of the strong force, which is described by QCD, which is a theory behind quarks and gluons. And the idea is that this theory is very hard to make predictions from. It's a very complicated theory, and by using this bootstrap approach, which is very general based on principles, we could try to learn something about the strong interactions. Okay, and this is it's an old. In particular, we're gonna look at very old expectations and things that have been relation, which turns out to be very constraining, and people didn't realize a way of making it systematic. So all of this is very broad. I'm talking about something that is very almost very qualitative. So we need to choose a fixed target. We need to choose a specific target that we can address. Okay, with the modern bootstrap. And the target we're gonna do is to try to put a bound on the cross section at finite energy. So a bound that can be compared with experiment, because the Frossard bound is at infinite energy. You cannot compare it with experiment. So the goal would be concrete progress on this question would be if we are able to find such a bound. Okay. And the tool we're going to use is this primal S-matrix bootstrap, which takes as input these principles that I mentioned: causality, which is analyticity, cross-asymmetry, and unitarity. And this is a numerical method that depends on two parameters. So this was proposed in this paper in 2016, and then there's a lot of authors that work on this. And there's like two parameters. There's n, which is the number controls basically how these principles are imposed, and then it's L, which is the number of constraints to impose unitarity, the number of unitarity constraints. So we're gonna do a numerical procedure to impose this systematically, and then if you take this to infinity, you are sure that you impose everything you could have. So there's two outputs from this procedure. One is bounds on low energy data. So I can put bounds on low energy coefficients like couplings, interaction couplings of my theory, and then you find bounds like this, that above a certain value of this low energy coupling, your theory is excluded. So this is basically the bread and butter of the bootstrap methods today, is to, for people that are not familiar, is to use these ideas to really exclude theories, extensions of my standard model, extensions of gravity, to try to constrain this possible space of theories. And then there's another very fun output, which I already mentioned, which is the amplitude. So the bootstrap tells you what is the amplitude that saturates the bound. And then this amplitude is an amplitude that is consistent with all the principles. And if we are lucky, this amplitude has a growing cross-section, and then we can try to achieve this thing that people couldn't in the past, which is to solve this problem. Okay? So let's see how we do. So I'm going to first talk about the bound on the cross-section at finite energy. Maybe let me stop here for questions.
No questions so far. At the end, we have some questions.
Oh, okay, perfect. Okay, perfect. So let's try to bound the cross-section at finite energy. So the first thing you notice is that if you choose a specific value of the energy, you see that basically you can have a delta function. So the cross-section is the imaginary part of the amplitude, and basically you can pile up many particles at one energy and just blow up the cross-section at that point. And so people noticed this in the past when they tried to making the Frossard bound rigorous. And so people thought that what you have to do is smear the cross-section. So there is integrated cross-section, which was proposed by Indurain. So you take your cross-section and you integrate in energy. So I start with a threshold. So these are low energies, zero momentum, integrate to some value of energy. And this is a well-defined object. And then there is a kernel that he multiplied, which is not really relevant. Okay, there's some reason just to simplify your life, but it doesn't really. It's not a crucial thing. And so this is what we're gonna do. And for concreteness, we're gonna do the simplest case possible, which is we're gonna scatter identical scalar bosons of a single mass. So there's a mass m, and there's identical scalar bosons. And you can ask, these are not protons, but at high energies, the Frossard bound is the same, regardless of the spin. So there's this notion that at very high energies for these integrated observables, average observables, it doesn't really matter, the spin effects. But of course, this can be improved systematically. So this is the result, okay? So this is the data I showed at the start. There is experimental data. And then there is an upper bound here, which is this red curve is what we obtain. So basically the statement is that the rigorous statement is that in any quantum field theory, which has a mass gap, so there's no massless particles in the theory, the cross-section cannot go above this curve. Okay, so any quantum field theory that has a cross-section that goes above this is not valid. It's not a consistent quantum field theory. And for comparison, we set the scale of 1 GeV. And you see there's like an order 10 difference, and this is very interesting because it's surprising that QCD is even like remotely close to this bound because we use very basic assumptions. So we have, as I'm going to show you, like we use some very drastic inequalities, and it's pretty interesting that that is the case. And in principle, this bound can be improved. So this is an important result because it holds at very high energies. It holds at any energy, and it's the first time that this data is compared to any sort of theoretical curve for 60 years that we've been measuring this. And moreover, in the bootstrap, as I told you, we put bounds at low energy. So, and this is a bound at high energies. So I need to tell you how we did this. So this is a strategy of the derivation. We have a first analytical step, which is to bound this total cross-section in terms of the low energy coefficient, which I call C2, which is basically the derivative of the amplitude in some low energy region. And the idea in this step is that we decompose these into angular momentum eigenstates, and there's going to be a low spin component and a high spin component. The low spin component we bound by unitarity. There's probabilities must add up to 1. And then the high spin part, we use the information of the short range nature of interaction. At high spins, you basically get classical scattering, long distance, and here we know that there's going to be decay of the interaction. And this high spin part we relate to the low energy data, which is this C2. And then also we have this relation. Now we can use the numerical bootstrap to put a bound on this low energy coefficient. Okay, so let me show you this technical slide. So you take this total cross-section, you decompose in spins. There's a low spin part, there's a high spin part. This is a sum, right? And I choose this L, is arbitrary. And then the low spin part, I have an upper bound given by unitarity. So unitarity tells me probability cannot exceed 1 or 2 in this normalization. So it must be smaller than that. And then you see, if I kept this bound all the way to infinity, it still gives me infinity because I'm summing L times 1. L 1 plus 2 plus 3 plus 4 plus 5, it blows up, right? So I need to say something about the high spin sum, and that's the part that we need to bound in terms of C2. Okay, and the idea of using C2 is that it obeys something called a dispersion relation. So there is an integral representation for this amplitude, not just a derivative. There is a Cauchy formula, if you might remember from complex analysis, that tells me that I could relate this to an integral, and this integral is this dispersion relation. So it depends on the imaginary part of the amplitude at the value t0, which is somewhere above 0. So it's information about the mass gap. So it's a value that is non-zero and is positive. And the idea is that this is almost the cross-section. The cross-section, if you might remember, is when I take these and they evaluate at 0. And here I evaluate at t0. So what I need to do is basically relate these two. And so to do that, you expand in partial ways. You expand in angular momentum eigenstates. And you get the same thing times some Legendre polynomial. So the same thing we had before, but now we have a Legendre polynomial. But in this region, this Legendre polynomial is a positive function. It's monotonic. So you basically can truncate this integral and move it outside, and you have a bound. You have an inequality. So I have an integral from 4 to s, which is exactly what we have here, and then a sum that starts at L, which is this high spin part. So I was able to achieve this bound that I wanted, which is a bound on the upper part in terms of C2 and the Legendre polynomial and everything else I know, right? So if I put the two things together, I find this bound, which is L times L minus 1 plus something. Everything I know here is valid for any value of L, value of T0. And now I have this function of C2, which I don't know. So the only way I have a bound now is if I find an upper bound on this C2. Sorry. And then once you find this bound, you can optimize over L and T0. Okay, so this is what we need from the numerical bootstrap. We need a bound on this C2 because everything else we have. So this is the formula. This is the plot that comes from the numerical bootstrap. So for any value of T0 that you choose, you can go all the way to the mass cap. So this is when you start producing particles. You need to stay below that. There is an upper bound, and the bound that diverges when you go close. But typically, the more you use of the mass cap, so the harder you take T0, you're using the fact that the interaction is more short range, so it's better. The bound becomes better if you take T0 large. But then also the bound, the maximum value of C2 also increases. So there's an interesting interplay. And when you play with things, you find that the optimal case is like T0 around 3 for this formula. And that's how you get it, right? So that's how you get the bound. Once you plug this bound there and you optimize you choose the best value of L and T0, you get exactly this curve here in red. Okay. And then analytically, if you take very high energies, you reproduce the Frossard bound, the thing that was known before. Okay. So I'm going to go to the last section of the talk, which is this amplitude. So I mentioned this output. I talked about the output, how we use this. Now I want to talk about this part. If you want, it's something a bit more fun because you can study the physics. I can stop again here for questions if there's any, or maybe, yeah. Or is okay?
No questions so far.
Okay.
We have some time for questions.
Perfect.
And I have two questions.
Okay. Sorry. So perfect. So okay, I finish the talk then. Is that okay? So let me go. Yeah. So let me go to the section. Yeah, it's because when I share the screen, I don't see anyone. So I don't know, because of this thing, I don't know. Yeah, that's it. Okay, so what is this amplitude? Okay, so we call this the Frossard amplitude because of the name. The Frossard is growing, right? This is bound. So this amplitude is the strongest interacting amplitude in the 2-2 sector. So the elastic amplitude sector, which is what we're imposing constraints on, is in this sector, is the strongest interacting amplitude because of the following reasons. It maximizes all the low energy coefficients. So all the couplings of the theory, which you can find in the action, if you write down an action, these couplings would appear in your action, and they're all maximized. So think about lambda phi to the 4. The theory, you have maximal lambda, maximal coupling. All the theories you can write down, all the couplings are maximal. So it's in this sense that it's a strongest interacting. And this is very surprising. Typically, you don't have an object that maximizes simultaneously all these couplings. And moreover, it also has a maximal growth of cross-section at high energies. So this is very interesting. This amplitude, when you observe it, it grows cross-basic constituents, and I smash them together. What is the result? And surprisingly, we don't know. It's one of the most basic questions we can ask. And in particular, I'm asking, what is the total cross-section from scattering to protons? And we don't know the result. But luckily, since the 60s, we start building these colliders, in particular hadron colliders, which allowed us to measure these observable, and I'm going to show you here. Okay, so don't be scared by this experimental plot. It's just, there's a bunch of dots, and you see there's a curve that grows, and this is the energy. So it's a log plot. And you see that the total cross-section of the proton collisions grows very slowly with energy. So these dots, for example, are around 50 GeV. This was measured in the 60s. And then today, for example, here the last dot is really comes from 2018 measurement at the Large Hadron Collider in Geneva. So there is no doubt that the cross-section grows with energy. And we have no idea why this is the case. So there is no model, there's no theory, there's no explanation for this behavior. And this is what we're trying to understand. Okay, and this is surprising because we know what is a theory of the strong interactions, which is QCD, but we don't know how to use it. Okay, so let me summarize what we know about QCD. Sorry, before that, let me mention this other observable, which is a bit more refined, which is the elastic cross section. So this elastic cross section is when I measure the two protons coming back, and you might have learned in QFT class. This is a simple observable, depends on two parameters: the energy and the scattering angle, which is represented by T. And this we also measure, and this is the formula. So you see, this is the value for different energies, and this is the value for different T's or scattering angles. And basically, we see something very clear, that it decays very fast, so it's exponential on the y-axis. So it decays very fast away from t equals 0, which is the forward limit, where things just pass through each other without deflecting. And then we see that it decays very fast, and it has some kind of bump, and then it keeps going, and then we start having experimental error. And for example, this feature of that is very peaked is called the diffractive peak, and it shrinks with energy. And then there is a structure which people call the deep bump structure. So there is no explanation for these behaviors. We've been measured since the 60s. Why are these features there, right? Why are they even there? And the reason why this is so complicated is because there is a hierarchy of scales. So essentially, I have a small momentum transfer. So these particles basically scatter at a very small angle, these protons. And because of this small angle of a small momentum transfer, we know that QCD at low energies confines, like the quarks and gluons confine into hadrons, which makes it much harder to describe. So it's a non-perturbative effect, which is confinement, which makes it hard. And then we have tools to describe confinement and this region, which is the lattice. For example, lattice QCD can simulate QCD. But the problem is that we are scattering at very high energies. So the lattice, this is where the lattice really does not work. The lattice likes to work at very low energies, and if I scatter things at very high energy, we can achieve this goal. We can compute an amplitude which has a growing cross section. So now we can study the physics. We can try to see this conjecture that this maximal growth was somehow QCD, and we can learn something about QC by this exercise, by looking at this object, this mathematical object. So that's what we're going to do until the end. I think I started a bit late, so probably I still have maybe 20 minutes or, yeah.
We have time, it's okay.
Okay, perfect. So then, so let me show you. So what I'm going to do now is to show you different observables from this amplitude. So I take this amplitude, I compute different observables I could measure experimentally. So one thing is that, one important caveat is that the numerics are very complicated. So this is a very computationally expensive exercise. So this is the hardest thing you can do with the bootstrap, because there's a lot of structure that needs to be generated, as we will see. So in the numerics that we had, we couldn't push this very far. So this is the bound. Even though the bound goes to very high energies, this is the amplitude that comes out. The amplitude that comes out sits below the bound, and it's more or less order 10, similar to what we see in QCD, but much lower energies. So this is like 14 GeV, right? And at LHC, we go all the way to TeV. So you see, and here, different colors show the convergence. And we see that we have a poor convergence at enough energies, and convergence is much better below. But you shouldn't care about convergence, at least at this stage, because every of these amplitudes, except this blue one, all these amplitudes have a growing cross-section. Clearly, the cross-section is growing, but very slowly. And for each of these examples, this amplitude is compatible with the principles, with the fundamental principles. So it doesn't really matter if it's the optimal amplitude. Each of these amplitudes is an example of a growing cross-section which is compatible with the principle. So we can still study it. So that's what we're going to do. So now let me tell you about the low energy part, which is the part where we have better convergence. Okay, so what do we see? So now what I'm going to do is compare. On the right, I'm going to show you typical experimental plots from QCD, and on the left, I'm going to show you output from the bootstrap. So in QCD, what you see is that at low energies, you see a bunch of peaks, and these are the resonances. So the things I showed you at the start of the resonance with different spins, like the rho meson, these are all extracted from this kind of plots. I have a cross-section which has a peak. For example, the Higgs boson at LHC is a peak. We measure, you take the mass, right? So this is what happens. In QCD at low energies, there's really a bunch of peaks, and then it settles down into some behavior, which is Regge behavior, power law. Okay, and eventually, if you keep going, it grows, right? So what we see in the bootstrap is a similar behavior. So we see that there's really a lot of peaks that are generated, and then eventually it keeps growing. So it's basically you'd see what happens here. So we are in this area, which is, and then eventually it keeps growing, right? And so this is why it's computationally very expensive. All this structure needs to be generated automatically. So I'm not imposing any QCD information. I'm just using maximized cross-section in a way compatible with principles. And this is all the structure it generates. So there's an emergence of structures that is hard to understand. But one thing cool about the bootstrap is that you can decompose everything in spins. So I don't have just a total cross-section like I have here experimentally, but I have the decomposition in all the possible spins and angular momenta. So this allows me to understand if each of these peaks corresponds to a given spin channel, right? So, for example, we see that there is immediately a spin to resonance at threshold. So this is a particle that has twice the mass of the particles I'm scattering, and it's a particle of spin 2. So this is the spin to particle I mentioned at the start from these arguments of the Frossard bound that you need a spin to particle being exchanged. We see that here, which is very cool. We see that consistency computationally, this particle is being generated dynamically from the bootstrap. But then I also told you another thing, which is the higher spin particles cannot come alone. They must come with the whole family of higher spin particles. And that's exactly what we see. You see, spin 4, there's another resonance. Spin 6, there's another resonance. Spin 8, spin 10. And looking at these, you would see they all belong to the same Regge trajectory. There's a single line that is connecting these particles, and we can try to check for this line. Okay, so what I'm going to show now is basically a more refined statement, a way of extracting these resonances directly from the complex plane. And I'm going to do this Shu-Fauci plot that people did at the start. So the plot where I have, on the y-axis, I have spin. On the x-axis, I have the mass. Okay? So this is the Shu-Fauci plot that I showed initially. So there's a lot of things going on. So let me go through them. On the y-axis, I have the spin. On the x-axis, I have the real part of the mass squared, which is the plot I showed initially, right? And you see these dots, all of these dots correspond to resonances. So particles. And the colors indicate the convergence. You see, convergence is better for these ones, where all the colors are on top of each other. And you can identify the particle, these dots we identified as the peaks that we saw before. F2, F4, F6, F8, they're all here. And these are visible as peaks. But then you see more structures. For example, you see G2, G4, G6, you barely see them in this plot. You see, they give you these little dips that you only see when you decompose in spin channels. Okay, you wouldn't see this here. So for example, in QCD, this cross-section, we wouldn't see these other structures, right? And there's way more things that we don't see. So this raises the question, where are all these things in the real life? Where are all these things in QCD? Why are they there? Like, why is the bootstrap putting all these resonances? They are there for a reason. They are there to make the cross-section grow, but we don't know. So this is the complete surprise that we had. There's so much stuff going on. So now let me try to look for the Pomeron. The Pomeron was this trajectory that intercepts around 1 when I take t equals 0. So now I'm going to zoom in on this region here below. And when you zoom in on this region, I'm showing here in the plot, you see there's a bunch of trajectories that are approximately linear, which is what we see in QCD, which is pretty interesting. And then there is an intercept above 1. You see there's this trajectory that intercepts a bit above 1, which matches the expectation from the Pomeron. So maybe there's a Pomeron indeed. So you see, asking for going cross-section and asking consistent with principles tells you there must be a Pomeron there. So this is pretty cool. But you see, numerically and computationally, we need to improve on this story. So I cannot say for sure. So we have a lot of error in this, in this value, even though it matches more or less the growth that we measure in the cross section. So there is a relation that is non-trivial, but this is the part we need to improve the most. So we can say for sure we found the Pomeron. And now the final thing that we see in this plot is this bunch of resonances here, which are basically the elephant in the room. What is all this structure that is accumulating? That is like accumulating around t equals 0, this structure that people did not expect at all back in the day. So if I zoom in on this area, this is what I see. So I zoom in here, and this you see better that this trajectory A prime basically comes and then comes back, right? So it does this, and then there's a turning point. This is very unusual. So we never see this typically, right? And then there's these all Z1, Z2, Z3 trajectories that are accumulating around t equals 0. So there's something going on here, because t equals 0 is the value that controls the total cross section, if you remember from the optical theorem. So these resonances are accumulating around t equals 0, and they are doing something that we don't understand. Okay. So let me recap. So this was a lot. There's a lot going on here. So let me recap here. So let me recap the observables in this regime of QCD, the soft QCD, which is total cross section, and then the resonances and the Regge trajectory. So I showed you already the total cross section. That was these peaks, and then I showed you also the resonances and Regge trajectories that we can extract with the bootstrap. And in particular, Regge theory tells me there's a relation between the two. So it tells me that the amplitude behaves like this. So the trajectories control the behavior of the amplitude. And the linear trajectory, which is alpha 0 plus alpha prime t, when I take t equals 0, it tells me something about the total cross section. This is the thing I reviewed before. And then, but you see, this formula has more information. There is dependence on t, which is completely gone in this observable, because I take t equals 0. So what is an observable that is sensitive to this behavior in t? And that's the elastic differential cross section that I showed at the start. So the elastic differential cross section is just the square of the amplitude. So it's basically the quantum mechanical probability, where you square the wave function. In this case, you square the amplitude. And now, if I take this behavior, I can plug it in this formula, and I have a prediction from Regge theory. I have that the total cross section, the elastic differential cross section, has a behavior that has a particular behavior in t, and t physical, which is physical scattering angle, is negative. So it tells me that the amplitude decays very fast in t. You see, it's exponential. If I go for t negative, it just decays very fast exponentially. And now you might remember this story that we see experimentally. So this effect is called the shrinking diffractive cone. And in particular, if I put it in the exponent, I see that there is this behavior like this. So there is a decay, exponential decay, and the decay rate increases logarithmically with the energy. And this is what people call the shrinking diffractive cone, that goes back to the 70s and the 60s. And this was basically one of the big successes of the Pomeron model, and why people still talk about it today, was that he was able to explain this behavior that we don't have any other explanation so far. So let me show you what happens experimentally. So ignore this jump here. And basically what you see is that there is, so this exponential plot here, and you see that exponential decay is just a linear curve in this plot. And you see that very well here at 50 GeV. In the 60s, we measured this, and you see that it decays linearly, very nicely, like you expect from the Regge trajectory. And then 30 years later, in the Tevatron, we measured again, and you see again linear behavior, but you see there is a slope that increases. You see a 50 GeV like this, and then at 1.8 TeV, it slightly changes again. And this slight change in the slope is logarithmic with the energy. It's very slight, and that's exactly what the log describes. So this model is able to describe this very well, which is pretty cool. So now we can look at this from the bootstrap perspective. And in the bootstrap perspective, we find the same thing. We find that the amplitude in the bootstrap, even though we cannot go to much higher energies, we see exponential decay with t, and we see that the rate increases very slowly also with energy. And of course you start to seeing some deviations which appear earlier compared to QCD, and you see there's also some deviations here. And so this is basically what the Pomeron model could tell you at the time, which was this decay, exponential decay. But eventually, as you can already see, this behavior was not enough to describe what was measured experimentally. So we start measuring more values of t to higher values, and we saw deviation. Let me show you these deviations. I already showed you at the start of the talk. So this is the most recent experimental data that we have from 2018. And this plot is exactly the same plot, but only up to 0.2. So it's just this section of this plot and where you see all the decay. And the decay is exactly what we see here. And all these curves are kind of scaled for visual clarity, but they're kind of on top of each other like they are here. But you see, then this does this, and then there is decay, and there's like a dip. It decays faster, and then there's a minimum, and then there's a bump, so the deep bump structure. And now we can look at the bootstrap also, and we see a similar story. We see that there is the decay that we saw initially, that we saw before, and then there is a minimum here. There's a minimum, and then there's a maximum, and there's minimum, and then it keeps going. And then you see there's a similar story, but here we don't know. Like in experimentally, we don't see more. But from the bootstrap, we see multiple minima, and something cool is that you see at lower energies, the minimum moves to smaller values of t. So I go to 13 TeV, this minimum comes to smaller values of t. We see the same, s equals 50, and then s equals 200, the minimum comes to the left. So there is something very cool here, because all this structure that comes out, we didn't ask for it. There is no QCD information on the bootstrap. So what this is telling us is that all these structures that we see, the diffractive cone shrinking and the deep bump minima, it seems like they must be there by consistency of physical principles. So this is pretty surprising, and this kind of opens the door to understand this better. So let me conclude, actually, because I'm running out of time also, but I'm happy to explain this part. So the last thing I wanted to say is that I wanted to conjecture on the fact that these weird trajectories maybe are related to this behavior here. I wanted to say that the explanation for these behaviors are somehow connected to these behaviors. And we don't have enough numerical precision to match the two stories, but you can do an analytical model, which is this white ring model that we have. And this white ring model has a simple formula in terms of Bessel functions. And by fitting these two parameters, which are the radii of this model, you can fit very well. You see that this dashed curve almost fits super well the initial behavior, and then it even predicts minima beyond it. And so this object you can analyze and try to extract the Regge trajectories. And when you do that, you find a similar story. You find that there is a Regge trajectory that does exactly this behavior that we see, that has this kind of curve that comes back. And actually this was interestingly proposed by John Schwartz. John Schwartz was one of the founders of string theory, and before that he was a bootstrapper. He was a student of Jeffrey Chu, and he already proposed that the Pomeron, at the time called Pomeranchon, could have been something more complicated than the simple linear trajectory. And so that the possibility is that these things that we see tell you that the full story is way more complicated. And probably, I would say, maybe if I'm being a bit too brave, probably these things are there in QCD and we just don't know yet. So maybe they are there in the experimental data, and there's a lot of resonances and things that we are not understanding yet, that they are related to this high energy behavior. So let me conclude. So we bounded the cross-section at finite energy for the first time, and then we explored this Frossard amplitude that comes from the bootstrap and compare with proton-proton data. We found a lot of qualitative similarities, even though it's not quantitative yet, because we did this very simple scalar toy model. We didn't inject any QCD information. We just stayed in the elastic sector. There's way more constraints, way more things we could impose. So what are the future directions? One is this phenomenological direction, which is trying to attack this puzzle of the Pomeron in QCD. So the Pomeron is these trajectories that we see here, these resonances that are responsible for the growth of the cross-section at high energy, and we don't know if these are there in QCD or not. So one way would be to input more information in the bootstrap, in particular the high energy cross-section data. It could be experimentally or it could be analytical using perturbative QCD. Somehow to inject in the bootstrap and then use the bootstrap and go to low energies and extract the resonances, extract the Pomeron. And this kind of games is exactly what people back in the day wanted to do with Reggie Fino. They wanted to use these resonances and a way to predict the high energy and vice versa. And now with the bootstrap, we can try to make this precise. And then theoretically, we saw that out of the bootstrap that the growing cross-section is extremely constraining, as was conjectured already back in the day. And we see now explicitly that there's a lot of features that are also seen experimentally that we see out of the bootstrap, like the shrinking diffractive cone, the presence of these deep bump structures, the presence of a very rich spectrum of particles at low energies. So this opens the door to use the estimated bootstrap as a tool to finally understand this high energy soft regime of QCD. Okay, thank you very much.
Thank you very much. We are asking if we have questions. Questions? I have two questions.
Yeah.
At the end. No, okay. I suppose there is no questions. No, sí, sí hay questions. Okay. I like a lot your presentation. I wrote my questions.
Yeah.
I already work with some strong sector that has bound states with composite dynamics.
Yeah.
So my first question is, does these ideas apply for any arbitrary sector working with the strong dynamics? For example, we know that you are working with a nonlinear sigma model, right?
Yeah, I mean, you mean like a model
perturbation,
like in chiral perturbation theory. You mean like like the pion.
Yeah, the chiral perturbation theory is an example.
Yes, exactly.
But if I want to apply these ideas with another nonlinear sigma model in an extended group of symmetries for describing the UV completion, how do I apply Reggie Phenom methods? Does it exist a bibliography to start with?
Sorry, what is the question? That if there exists a bibliography?
To work in another nonlinear sigma model with another group of symmetries.
Yeah.
That could not be the group of QCD SU3, but it could be SO5, for example.
Okay, well, for example, a completion that integrates the other sectors of the Sonar model, for example. Like, I see. So let me just say that the tool we use, which is this bootstrap, does not assume anything about the symmetry. Does not assume anything about the UV completion. So it's completely agnostic. All you need to include is the particles that you scatter. In this case, we just use a single scalar, and you can say, oh, maybe that's a pion. Maybe that's, typically when you have the symmetry breaking, it tells you there's a bunch of goldstones, and that's what you should include in the bootstrap. In this game, I just played a very simple toy model of one particle and asked for the growing cross-section, and then you see all of these structures emerge. Now I should do the proton, I should do fermions. But if you want to study what you're suggesting, which it seems like you want to study the low energy dynamics of some like strongly coupled sector, like the nonlinear sigma model, then there's going to be some, like the Carl-Lagrange, there's going to be some pions that when the symmetry is broken, there's going to be some goldstones. You could study those. That's where you inject information about the symmetry of your theory, like is in the spectrum of particles that you scatter. And people have mentioned these, and people have done this in the literature. There's this snow mass report, this review on the estimated bootstrap that says what people did, but people have done the pions. People have even thought about the Higgs, and you could inject experimental constraints, like things that you know at low energies, and try to, see other things.
Okay, yeah. But if I want to start with another group of symmetries bigger than the group of QCD, what is the bibliography to start with for this method? To apply this method in another group of symmetries bigger than.
But I mean the
QCD.
So I don't understand if you want
to describe another bound states with the techniques of Reggie, tracking the trajectories for analyzing the resonances of the new strong sector.
Yes,
but
yes.
And the strong sector is another sector that is not necessarily the sector that emerges in QCD, but is a sector that is proper for model beyond the standard model.
Yes, yes, yes.
With another Lagrangian that has new resonance fields.
Yeah, yeah. I mean, in the end, what you need to do is to understand the symmetry breaking pattern, understand the particles that emerge in the infrared. So what do you know? Like in the Carl Lagrangian, there's pions and there's kaons, and then you can include those in the bootstrap. That is telling you the information about that. Now, if you want to have a bigger group, then there's probably new particles, new Goldstones that you're going to have. For example, if you do the pions here, and you use the bootstrap, you're going to see the emergence of the raw meson naturally as a resonance. You could try to do a similar game in your story. You just need to know the symmetry breaking pattern and what kind of Goldstones or low-lying lightest particles emerge. If you don't know that, then it's more complicated.
Okay. But it can be at the end.
Sorry?
It is a general framework to work in those theories too.
Yeah, of course. You can, it's completely general. Yeah. You just need to understand because you don't have access to a Lagrangian in the bootstrap, you just have access to the observables, which is the S matrix. So all the information you need is the spectrum of the particles, at least the low-lying particles. Yeah.
And the other question is, I don't get if this method was for the lattice model or the model of fields in the nonlinear sigma model.
The lattice model
in general for fields.
No, this was this was quantum field theory, right? So this was so in the lattice you don't even have an S matrix. You don't have a scattering amplitude. I mean, you need to do. I mean, you do have people measure, but you need to do the continuum limit, and it's tricky. You need to relate the lattice data to the cross section and to the phase shifts that you measure. Okay. So this bootstrap setup uses general principles of quantum field theory. So in that aspect, is directly quantum field theory. Yeah.
Okay. Thank you.
Thank you. Okay. Any more questions, or is it good?
Hello.
Hello.
Nice talk.
Thank you.
My question is that if Rage theory is only for non-perturbative theories, I mean bootstrap or.
Yeah. So you mean if Reggie theory is only for non-perturbative physics?
Yes.
If you do string theory, for example, I mean, depends of if the spin. You see, the difference is if the particles that you see in the higher spin particles are resonances or stable particles. If they are resonances, you typically need non-perturbative physics. But if they are particles, you can use just perturbative theory, like for example, string theory. In the Veneziano model, there is a lot of higher spin particles, which are the string excitations, and we see them explicitly. So you can do that. So Reggie theory applies in both cases, as long as you have higher spin particles.
With higher spin.
Okay.
Yes.
My final question is, what
Thank you.
what program did you use for your graphics?
For the plots?
For the plots of working with Regis.
We use the mathematic plots, and then we edited them using Keynote. Actually, the one for slides, you can just add the arrows, and it's very convenient. Yeah.
Okay.
Okay.
Thank you again.
Thank you so much,
Yes,
and enjoy your time there. Thanks a lot for inviting me.
Thank you.
Bye bye. Thank you.